Hello, IB. This is 9A, area of triangles, and we're going to look at three specific types of triangles to cover all possibilities. And just to start off, we'll take a look at an applet to show you guys what happens with area of a triangle as you change various other aspects of the triangle. Now, I'm sure you've probably seen this idea before, but if you keep your eye on the area of a triangle, so 1/2 base times height, as I move the height around this altitude, if I keep it, let's say if I try to make this a right triangle, notice we've got an area of 45 and I have a height of about 6. If I make it more of an acute triangle, again, my height's about 6, my area is still 45, and if I drag this height outside the triangle, I still have a height of 6, my area is still 45. So even though the shape of the triangle has changed from a right triangle to an acute triangle to an obtuse triangle, I still have the same area. So the formulas that we look at today are going to work for any triangle, and we're just going to show you guys why. So taking a look at the right triangle to start, triangle ABC, across from the large C, so angle C, I'm going to label this side little c. Across from the 90-degree, we'll call this little a, and we'll call this last side small b. So the first thing that we notice is that if I look at where the theta is placed in where angle C is, we can say that sine at angle C, or theta, is equal to C over A, little c divided by A, so opposite over hypotenuse. Since we know that the area of a triangle is 1/2 base times height, I'll just write this up here. We know that one. We're going to take a look at this C value as representing the height. So this little c, if I want to isolate little c, I'm just going to multiply by A. So A times sine of big C, which is where theta is equal to little c, which is representing our height. So now if I write down my area of the triangle, I can represent that as 1/2 base times the height. And my height, again, is this little c, which is little a sine of big C. So I wind up simplifying this down to 1/2 a b, and then sine of c. We'll notice that you have a similar idea, and again, this is just to find the area. So the area of this triangle is 1/2 AB sine of C. Again, that would help us out if we didn't know what the height was, but if we were given an angle, and then we can wind up using that to find the area of the triangle. So similar idea in the second case with an acute triangle. We can call this little c, little b, little a, and maybe this is our height, so maybe we'll use h on this one as well. Again, I can use sine of big C, where the theta is equal to, we'll call that h divided by b. So I need to know what the height is if I'm going to find the area of the triangle. So my height in this case would be little b times sine of big C is equal to the height. So now when I wind up using my area formula, I'm going to have 1/2 the base times, my base, excuse me. All right, so for this one, sorry about that, my base is A, so base A multiplied by the height. Again, so my height is little b sine of big C, since we found it right here. So if I simplify that down, I get 1/2 little a times little b sine of C. What I'm starting to notice is if I look at where A and B are, they are the two legs that make up the angle C. If I look back at the first example, little a and b, again, are the two legs that make up this angle C. So I'm starting to get the same formula of these two legs that I need to use and the one included angle. Last case, if I look at my height, and for this one it's going to be outside my triangle, what I'm actually looking at here is, for me to use sine, I need a right triangle. So I'm going to have to focus in on this little piece outside of my actual triangle that I want to find. So if I take a look at this one, to find the height, I'm going to need this angle right here. So if I know that this interior angle is theta, then I can use 180 minus theta to represent this exterior angle. So if I wind up saying, all right, let's say sine of 180 minus theta is equal to, and I'll say opposite, so over hypotenuse, so this is opposite of h over hypotenuse. So in this case, my hypotenuse is little b. I didn't label my little c, little a, and little b. So again, my height is going to be represented as little b multiplied by sine of 180 minus theta. Now, luckily, the last couple days, we've been talking about how sine of 180 minus theta, if we think about our unit circle, so here's theta, here's 180 minus theta, all right? Those two values are the same for sine because they're both first and second quadrant. Sine is positive. So sine of 180 minus theta would be the same as just saying sine of theta. All right, so now if I wind up writing my area formula, I'm going to wind up with the same exact equation. 1/2. The base in this case is going to be a as well, and then multiplied by the height, which is b sine of theta. All right, and theta just happens to be on the c corner, so I could also represent that as c. So 1/2 a, little b, and sine of c. So since we could really have written these letters on any of the vertices, and you don't have to use ABC, you're going to see this with all different letters, and they'll be labeled however you set them up. So really, little b, and using sine of big C. You could also find it if you relabeled it and use little a, little c, sine of big B, and then little b, little c, and sine of big A. So however you set up your triangle, really all we're looking for is the two sides and the included angle. So in other words, the two side lengths, and that make up the angle that's between them. So taking a look at this example, given the triangle at the right, find its area. Express the area rounded to 3 decimal places. So we have two sides and we have the included angle. So again, these could have been labeled however we wanted to, but let's go ahead and use the formula that we just derived. We have the area is equal to 1/2 little a times little b times sine of c. Opposite angle A is always the side little a. Opposite angle B is always the side little b. Opposite angle C is always the side little c. So when we refer to little a and little b, we're looking at 18 and 12. So 1/2 times 18 times 12, and then sine of the included angle, 94. Once we have that set up, we can go ahead and use our calculator to tell us what that value is. Remember, this is an area. We weren't told any units, but technically we have units squared. So we rounded to 3 decimal places. Always make sure if we're using degrees, your calculator's in degree mode. The second example would be a great one for you to pause and try to set up on your own. We have two acute triangles. Let's see. Yep, we're not sure acute. They can't always go from the diagram. They look like they might be. So we'll go ahead and put two of them together, and we're really finding the area of a parallelogram. So, but all we're given is two sides and the included angle of 60. So the first thing I'm going to do is find the area of one triangle. So triangle ABD, for that area, I'm going to use 1/2 of 10 times 16 times sine of 60. Now this is a fantastic example of what you are able to do now without your calculator. So without my calculator, we've been practicing over the last few days that sine of 60 degrees is really square root of 3 over 2. So now without our calculator, we should be able to replace that sine of 60 with root 3 divided by 2. So again, think about how that simplifies, and we get 40 root 3. So 40 root 3 is just the area of this first triangle. So if I double it, I wind up getting the area of a parallelogram. All right. And again, this is square units when we're talking about area of a parallelogram, when we're talking about area. So if we wanted to use the same idea of the formula that we have here for a parallelogram, we would just take away the 1/2. For the last example, go ahead and try to set up a picture of what this looks like. So when you're not given a diagram, some of us might have set up an acute triangle, and some of us might have set up an obtuse triangle. If we have two sides that are set, then that third side could either be relatively short, and the triangle could be acute, or relatively long, and you could have an obtuse triangle. So what we're looking for is actually two possibilities for the angle in order to give us the two possible triangles that I could have an area of 50 centimeters squared with two sides being 10 and 11. Go ahead and set up the formula and see if you guys can figure out what those two values would be. So if our area is 1/2 the two sides multiplied by sine of the included angle, which we do not know, we're given the area, so I'm going to substitute the area as 50. Then my job here is just to isolate for theta. So once I solve for theta, I get 65.38. So that would wind up being the angle for this acute triangle. So in order for me to find the other angle, I'm going to wind up taking 180, as I know that sine of theta and sine of 180 minus theta will still give me the same values. So let's go ahead and find my second possible angle for the obtuse triangle. So my second possibility is for theta to be 114. And just looking back at the directions, one decimal place, so 65.4 degrees, or I could have 114.6 degrees. So I have two possibilities. So I can either use the formula to work forward and find the area, or I might be given the area and I need to work backwards to find the theta. Have a good night, guys.